Okay. So I'm Luca Graziani. I'm working at the University of Rome La Sapienza, and today I'm going to talk about this new strategy that we adopted for our simulations of galaxy formation and structure formation, combining them with machine learning algorithms. So the problem is as following. You wanted to simulate a portion of the universe, which is large enough to capture the statistics of structures. So what I'm showing here is a typical cosmic web, which is a web of structures in the universe composed by filaments, as you can see in green, and knots. And the color palette represents the number density of the gas structures present in this volume. The size of the volume is 50 comoving megaparsecs. So it's quite large, but it's not extremely large. Consider that if you wanted to really capture a global statistics from a universe volume, you should go to 500 comoving megaparsecs. But then you don't have the resolution to see small structures like this one. Okay. So this is an intermediate size volume, which is capable to see a number of structures and see the details of these structures. So you can investigate properties of single galaxies inside the volume. Things that you cannot see if you go at large. Okay, you just see assembly of galaxies. You cannot disentangle any single structure.
You're not looking at the black.
We are not. Okay, is that okay? You see the slides, I guess? Thank you. So what I wanted to say, probably this is not the best place. Okay. So, I mean, the point is as following. You have different structures. You have overdense regions, which corresponds to green or red colors, if you can see them. Inside the entire structure, you have a lot of voids, which correspond to a number density lower than 10 to the minus 5, 10 to the minus 6, even 10 to the minus 8. So there is a large excursion in this gas density field. And the point is, do you recognize these structures when the number of structures becomes million structures, million voids, etc.? So another point, if you can recognize where the galaxies are, probably they are inside overdense regions where the glass clumps and you start seeing this orange or red structure, and you zoom in, the picture that you see is it is shown in these side panels here, okay? So it's the same number density, gas number density, and this is how a typical galaxy in the high redshift universe appears. A lot of clumps, basically. Most of them are forming stars. At the center, you see a specific population of star, which is called POP3 population of stars, which is the first generation of stars, which is particularly important because it's not observed, it's just predict. And we believe that in the next 10 years, maybe we will have an evidence of the existence of this population of first stars by the James Webb Telescope, which is operating right now. Okay. So if you can see the galaxies, you see a variety of structures. They look really different. Each galaxy has its own properties, its own gas distribution, star distribution, and whatever. So what do you want to do with this? Consider that a simulation like this takes at least 4 months before having this picture, okay? So once you compute it on large number of processors, a monster like this, you want to check if the galaxies that you obtain are real galaxies. They look or they appear in their baryonic properties as a real galaxies. So what we do is to follow the evolution of our galaxies in different planes. For example, here I'm showing the main sequence of galaxy formation, which is the relation connecting the stellar mass of a galaxy with the star formation rate, the capability of this galaxy to produce new stars, okay? So this is a famous relation, which is well investigated in the low redshift universe, because you have a lot of observations. But the point is, can we predict the existence of the same relation in the high redshift galaxy, and to compare with recent observations or future observations of the James Webb Telescope? So what you have here, following this figure from top left down to bottom right, is the redshift evolution of our galaxies, which are shown as a gray points. The violet line is this revelation, it's the fitting, basically, linear fit. And we are showing the progress in the buildup of these galaxies down from redshift 10 down to redshift 5. As you can see, more and more galaxies are forming. If you follow the redshift evolution of your universe, they distribute basically on a relation, which is the main sequence. Our main sequence is the violet line. And you want to compare our predictions with a sample of observations that we have right now. So all the points are different observations taken from different telescopes. But what is exciting here is that the white stars, the violet and the cyan stars, are points from the JWST early science observation. So JWST galaxies look as galaxies quite well, distributed across our main sequence. So this means that your simulation is not just imagination. You did put the right law of physics. You did put at some point, things make sense. Let's say in this way. And you want to investigate a little bit more because, you see that you have a relation like this, fine. You see that there is a scatter, and the scatter increases when the number of structures increase, which means that there are a lot of physical processes at play, changing the properties of a galaxy at fixed stellar mass. It could depend on the environment. It could depend on the efficiency of physical processes. It could depend on the presence of a black hole, which alters the normal evolution of a galaxy without it. And all this physics is called by astronomers or cosmologists as feedback. So feedback is everything which is changing or shaping the story and the properties of your galaxies depending on the kind of physics at play. So you can have mechanical feedback when you consider hydrodynamical processes. The gas is moving, the gas is clumping, the gas is doing shocks, hydrodynamical shocks. You can have radiative feedback when you have stars. They propagate radiation, which can alter the gas, ionizing, eating, and stuff. Or you can have chemical feedback. Because if you have stars in your galaxies, they would evolve. They would release metals into the gas. Having a gas with metal means changing the properties, the cooling properties of the gas because of the recombination lines, because of all the atomic processes at play when heavy elements are present. So all these feedback processes can be tested into other relations. Here, for example, I show the stellar mass. We always start with the stellar mass because it's the component which is making a clump of gas a galaxy. If you don't have stars, it's difficult to talk about galaxy. And we connect the stellar mass with the dust, which means are the stars that you produce in your galaxies capable to produce the right amount of dust? Dust is produced in the local universe around supernovae, primarily. Probably AGB stars can release dust in the interstellar medium too. And there are theories saying that dust also changes and evolves inside the interstellar medium. So are you capable to reproduce all these processes in your simulation? It's difficult. It's hydrodynamics plus chemistry plus everything. So let's try. So the great are our galaxies. The panel distribution is as before. And you see how many observations we do have in the high redshift universe. Practically nothing, 2 points. Some points at redshift 7.5. But you see that our points continuously continue to distribute on a sequence which barely gets the point, at least the meat or the trend. And we go better and better when we go down to redshift 5, which means that at some point, the part of the relation that can be constrained by observations is not okay, but reasonably okay. So what is the reason why this has such a low dust mass, or the other galaxies an excess of dust mass? That's physics that we want to understand by using simulations, because you don't have right access to this data by observations. Okay, another problem. So you say, I said that our stars are capable to produce the right chemical properties or something which is absolutely reasonable. But I also said that there is a generation of first stars which is not observed, and we would like to understand what are the predictions of the simulation in order to provide a feedback to observers, like what is the kind of galaxy that you should point to in order to have a maximum probability to catch a first star? What is the kind of galaxy stellar mass in which probably first stars continue to produce? So we place figure. So you have all the galaxies as a gray points, and the red galaxies are objects in which first stars are present according to our models. So we can classify these galaxies and provide useful information to observers if they are reasonably correct. But the problem is as following. I recognize the galaxy inside the large scales. These are 50 co-moving megaparsecs. In order to see this galaxy or reasonably resolve its components, I have to go down to kiloparsecs, 20. But if you really wanted to see the first stars, where the first stars are placed inside your galaxy, you have to zoom in inside. So doing this extraction in a very large volume, which could contain million galaxies, is a complicated problem. It's really complicated. So it's not just, let me finish this sentence and I will. It's not just running the simulation. The simulation is done, is there. But if you need 4 months to run the simulation, you will probably need 10 months to do the post-processing, to recognize the structures, to find the objects. Okay, please. Sorry? The resolution is mass is not extremely high. It's 10 to the 5, 10 to the 6 solar masses per particle of gas. These are not stars, these are stellar populations. We can just simulate agglomerates of stars, stellar populations. Thank you, correct. So I think I've shown that the problem of understanding your simulation is even more complicated than running the simulation itself. Another example, you see, these are different galaxies. Again, seen in different properties. You have the gas, the dust, second panel from top. The oxygen, second panel from top, atomic oxygen. And the dust, third. And this is the stellar distribution. So stellar particles are these ones embedded in this complex structure of gas, dust, and whatever. So before talking about how machine learning can help us, even if I think you already understood that pattern recognition can make a difference here. Let me show you how the simulation is working. So the method that we are using is called SPH. We then discretize in a Monte Carlo fashion a continuous field of a fluid, which is dark matter, gas, baryons, whatever, into particles, different type of particles. We follow them by running the simulation and following the dynamics of the particle according to the particle type. So if you have a dark matter particle, you just use gravity. If you have a gas particle, you move it according to the Navier-Stokes equation, discretized and simplified. And if you have stellar particles, you just use collisionless dynamics, basically. You release the metals. And basically, this method is quite efficient in spanning scales. You see, people are simulating the large scale structure, but you can also resimulate single galaxies or even the center of a galaxy around a black hole, the third image from top. But also have pitfalls. Okay, look at how our method, which is this one on the right, predicts the gas distribution comparing to other methods based on grids. You see? The number and the kind of structures predicted is heavily affected by the method in use, because discretizing fluid dynamics equations is biased by the method that you adopt. Okay, and this is where and when your method works quite well. Supersonic turbulence, acceptable, let's say. But if you go to subsonic, it's a disaster. It's a total disaster. It doesn't work. Okay, so this means that from one side, you want to span structures, you want to move across the scales, and from another side, you know that when you go to scales in which subsonic turbulence works, you don't predict anything. So let me summarize in this way. From one side, your method is capable to span scales down to a certain level. Because if you wanted to go deep and deep, at some point you enter into a domain in which your method doesn't work. It doesn't predict the right gas distribution. But at least you span 3 scales, which is not bad. All right, that's an example. Interesting, and I wanted to comment a little bit. It's something which happens continuously in our universe. Galaxies evolve by merging. They have close encounters, they merge, and they form a new galaxy, which is summing up the properties, roughly speaking. So if you wanted to follow this process with your method, you have to follow the merging of the dark matter components, which is on the top. You have to follow consistently the gas component merging. You see the differences. Dark matter doesn't go through collisions. The gas is going through shocks. Okay. And the structure appears in a different way. But you also wanted to merge consistently the stellar component, which is the bottom panel. Okay. And you follow the process in time from left to right until the merger is complete, basically. So this is one example of a process that we would like to track during our simulation, because if you are capable to capture where this occurs and when, you can say to your simulation, listen, the resolution in this region, when I would like to capture this process, is not appropriate. Increase it dynamically. So this means that when running the simulation across the scales, if you have an information where the most interesting processes that you want to track occur, you could adapt a little bit by selecting appropriate boundary conditions. I don't want to go into technicalities, but the idea is that you don't run blindly because it costs a lot. You would like to say, okay, I wanted to reproduce a region of the universe which is large. I wanted to have my statistics to compare with the observations, but I would also like to have the capability to investigate where the situation is more interesting by increasing the computational power, by focusing computational power there and capture these processes. Because that's a mystery. Galaxies grow mainly by this process. I mean, at least 60% of galaxies use this process to grow. So that's important to track. Okay, so let me go to the infamous machine learning stuff, please. Okay.
You said that you want to detect the moment in which the thing is happening.
You want to understand when, which time, and where, in which part of this 50 moving megaparsec volume, a kind of merging process between two galaxies occur. But if you know the region, you can say to your simulation, your resolution is not appropriate. but there is an insight that some process is starting there. So increase the simulation, increase the number of particles and decrease their mass. But you have to rerun everything. You have to recapture. I wanted to do it on the fly.
Yeah, but integrate the information of, I think that the thing is evolving.
Uh-huh.
You are just formulating the question at the end of the day.
Yes.
So can you use a example of one?
You can use a dump, but your simulation will continue.
Yeah.
And before understanding that the merger was there, your simulation reached the end of the merger.
And you take the dump and you start from that.
Yeah, and you restart. But if a simulation requires 4 months for each merger, let's say it's incompatible with the publication process.
Okay, thank you very much.
Got it? Okay, fine. I mean, it's a practical reason. I mean, we live in a real world. I mean, we cannot wait bazillion years to capture one merger. So machine learning can help. Ah, sorry, I didn't see. You wanted to ask a question? All right. So let me go through this business here. Okay, this is a popular picture on the internet, which I basically don't like, but it's popular, so I use it. It's wrong. I agree with you. Another popular picture is there. Is that one? Huh? The first sentence is correct, I guess. So first of all, machine learning is not artificial intelligence. It's a complementary stuff. And I like the idea that there is no inclusion, there's an intersection. You can use method from machine learning to help your artificial intelligence work better, but it's not the whole story. There are a lot of features on AI or machine learning which I will never use. Natural language processing, well, at least you want to talk to your simulation, but easy to use a shell. But there are features which are interesting. Unsupervised, supervised, clustering, or reinforced learning, which can be used in that context. Because if you already have a lot of simulations, you can train a network. If you already have done a lot of work on post-processing, and you think you know how to recognize at least the set of properties which could minimize your cost function, I mean, at some point in the network, in the neural network, you can train a network quite reliably. And then you could go through an unsupervised state, okay, to see if the machine learning algorithm is capable to inform you when and where a pattern is recognized. Or, that's the best, this is what I like, an interaction between your algorithm and your simulation. Meaning, I'm moving particles. My learning neural network, which is supervising me, is telling me, look, this region is promising. Follow it, increase the resolution. Don't follow the rest, just follow this. And I will continue to run it, and my machine learning algorithm will continue to supervise it and provide information on what is relevant in there, okay? So it's not AI, but it does not imply interaction necessarily, but we have this supervised, unsupervised, and constrained path, which is quite clear, at least in the theory of machine learning, and we can use it. So clearly, I mean, the first thing that I want to use is pattern recognition, because I want to recognize my structures. That's quite clear. And what does pattern recognition means? Is to identify the regularities in a given data. I'm done. That's easy. Everything is highly automated, is efficient, quite efficient for real-time problems, which is what I'm interested in, and has some predictive capability, okay? So you can use clustering algorithms for an unsupervised learning, if you can rely on some similarity metrics, or you can classify by training your network with the accuracy criteria that you define as appropriate to recognize your galaxies or whatever you want to recognize. Example, I have my structure. Can you recognize this overdense region? Can you disentangle it from this void, or understanding what is chaotic because it's just full of filaments, doesn't have any specific pattern, okay? And how fast are you in doing this? That's a question that I asked to my machine learning algorithm. Second question, if you can recognize high level, large scale structure, can you go inside, recognize cosmic galaxies, can recognize their shape, stellar content, their star formation rate, etc. So can you tell me in which part of my main sequence the galaxy that you focused on is placed? So that I can say, okay, that's a good candidate for an observation to compare with. Otherwise, what we are doing right now is a blind approach. We run bazillion cubes, collect the statistics and search inside it and say, oh, I'm lucky, I have one. So this is what I want to avoid. Same thing with the mergers. Look how complicated is the galaxy merger process. Many galaxies are combining all together in time to create big galaxies. Is that predictable at some point? Do you see regions in which this process occurs with a higher rate, in which I should focus because it's more informative? All right, other processes, the feedback, that's physics, that's a gas physics. You see here a map of the gas, and all these arrows are velocity fields. At the center, you see a galaxy. Do you see a wind? Probably. Something moving around here, escaping the galaxy. That is one thing that if I can recognize where winds are, I will understand the process of metal pollution. That's a reionization simulation. This is a quasar. It's ionized bubble. And these are bubbles created by stars, really confusing, overlapping, etc. So can you recognize the bubble of a quasar in the mess created by stars? Or do you see a wind here? Is this a wind, or is a galaxy irregularity by combining gas distribution and velocity fields? Okay, so I think that you already understood why machine learning can help in recognizing all these patterns on the fly. Just let me make a point really fast. Machine learning can have a supervision, okay? But there is an intrinsic difference in supervised machine learning, post-processing, and on the fly. Because post-processing can be accurate as you want, can be optimized, but it is not trainable. The simulation is done. What you get, you have it. That's it. And it doesn't help to predict anything unless you rerun the simulation. On the fly, that's a better solution. So if you can wait, I don't know, 3 years before having a paper, good luck. So the intermediate solution is get a help from machine learning. So that's how this works. So we have our simulation at specific redshift, which is time evolution is from top to bottom. A specific situation, a specific cosmic web. My simulation asks to monitor regions to a neural network, which provides suspect patterns, which have to be confirmed, because the time you need to identify the patterns, the simulation will continue to evolve. You cannot stop it. Once you have suspect patterns, you go back to your simulation, you say, okay, follow these suspect regions, increase the resolution. Let me see if there is something interesting. And you move them to the machine learning, which verifies and tells you, okay, go deep. Okay, that's a promising. Once everything is done, you go back to the simulation and you can have to zoom in to reduce the time of this resolution or to dump some interesting data. Okay. I will tell you after the last slide, otherwise it's gonna kill me. Okay, so this is just a technical detail on how all this framework that we are building in Rome is implemented. We have the cosmological simulation implemented in C++. This is fast and efficient and whatever. We have a communication layer through network. TCP/IP works okay. You communicate with a Java layer, which is handling our machine learning by using this framework, which I like. Deep learning for J is free, is open, no companies. You can modify it as you want. And the continuous interaction hopefully will provide us better simulations. Thank you very much. Sorry for being late. I keep my conclusions here. Get any questions?
Thank you.
Take your
Question.
questions. Okay. Another one.
The microphone.
Okay, this trend is confirmed, then you increase the resolution of this.
Is you will never do it with a single threshold. It's a combination of parameters. You check at the same time. You have to ask your neural network or wherever you wanted to use to check velocity field first. So the dynamics is compatible to something that you think is an assembly process. You are easy to find a center of mass. You are easy to find a center of movement. Okay, and then we have a range of number density that we know, which is constrained by observations. We know that galaxies, they live, interesting galaxies, they live, star forming in very high dense regions. So you can skip a large part of the domain, which makes the problem feasible. If you want to recognize a filament, I have no idea, because filaments are everywhere. They span, I mean, large, but who cares? Filaments are not observed. So for now, galaxies are okay. And they will be observed by the James Webb Telescope. They are observed right now. So that's our target.
Other questions?
If you want more technical details, we can discuss. Java side.
Sorry, very interesting. I have a question regarding the machine learning aspects. Like at the end, I didn't quite get, like, have you done a supervised learning approach or a reinforcement
We
learning?
train our algorithm in a supervised way.
Okay.
Because we already have a lot of data simulations, and we already have, I mean, by chance.
How is the data set
with
constructed?
some luck, we have, let me finish. We have simulated galaxies which look very similar to observed galaxies.
Okay.
So this is a very rich and powerful set of data to train your algorithm, because at least it provides you the capability to recognize something which will be observed. Otherwise, any simulated galaxy has a value. I mean, you can simulate, I mean, your image if you want to. I mean, that's computer stuff. Okay. So we first train the networks. And it is not finished because it's a very long process. It gets confused by everything. Even a stream of gas escaping from a galaxy will tell you, oh, that's a filament, because it has an elongated, I don't see any center of mass, so it's quite long. So we have something which is trained, and now we are trying to challenge the network with randomly sampled cubes, whatever. And it works, honestly, 40% right now, but we just started. So it's a long time business. I mean,
So like, how do you label? I didn't. How do you label, like, the data set? How is it constructed? Like, you have the.
A galaxy is labeled by an assembly of processes, of properties. If you see mass of star, probably is a galaxy. If you see a certain density, probably is a galaxy. If you see a specific center of mass across particles, I mean, if you use clustering algorithm, it's easy. I mean, it's just geometry, okay? But this is not sufficient. Once you identify the cluster, you have to be sure that this is a galaxy. Otherwise, a cluster, I mean, a cluster of dark matter is everywhere without having a single star inside. So you identify the cluster geometrically, gravitationally, whatever. Inside, you check that the right labels identifying the real galaxies are present. Otherwise, it doesn't make any sense. So it's a clustering combined by classification. Basically, it's like this.
Okay, thank you.
That's why it's so slow.
Thank you.
Other questions? I have a question. I haven't understood I mean, you say that you need at a certain point to understand when you got the ongoing merger so that you can increase the resolution of your simulation. And then you want to do this with the artificial, well, with the algorithm that you are showing.
Recognition.
This means that you must have a training set where this was already done in a sense, which already done properly.
Yeah.
But how did you recognize and do the super resolution in the
But
previous?
listen, if I have a set of simulations, assume this, I have a set already done, post-processed, I recognize my galaxies. If all my galaxies at least respect and follow the scaling relations, these galaxies have a chance to be observable, okay? If I already check my simulations and I know that, I don't know, say certain % of galaxies are very similar to the ones observed, this is a quality data to which train your.
No, what I mean is that you must have simulations which were made at a resolution higher
And this
than
is
you
why we
want to
started.
do
This is
now.
why we started now.
you
At
want-
least you have to be sure that your algorithm reproduces real stuff, and then you train a machine learning stuff to say, okay, train on this because it's real. We don't have real data.
Yeah, no,
We are
so-
simulators.
No,
I'm
just to
sorry.
understand. Done now to do simulation at the resolution lower.
Yeah, but lower.
the
10 to
previous
5, 10 to
simulation.
6 is not so low, but sufficiently
then
high,
you-
low or high, whatever you want, to see, okay, the galaxy that I see in post-processing is a real one. Has the same properties that the one observed by Halma. But as you saw, I mean, the points are well distributed across our relations. I can at least find 3 candidates for any observed galaxy, 3 simulated candidates. What do you want more? Yeah, I mean, the problem of the JWST data is that they are released with a super fast, unreliable quality. So the data that you saw, don't ask me if they will be confirmed in a month. But there is always this publication business, you know it better than me, you know? But we can wait. I mean, the point, no, let me do this point. That's an important scientific point for the students, not for all people, they know it. We never confirm our simulation with a single data set. I mean, here you have Alpine. This is quite robust. You have Rebels. You have single galaxies observations, not survey, single galaxies observed. And we combine all together because what is interesting is a statistical trend. And the data is so sparse and so reduced that you don't have it. So don't ask me if these exciting points, they will remain there, but at least I agree with this, or I agree with this, which is quite robust, first. Second, don't compare your simulation at fixed redshift, because it doesn't tell anything. It's chance. It's good luck. I mean, you found a moment in which, I mean, if your simulation agrees for at least 2 gigayears with some evolution, that's something which makes sense. Not a single point which probably, I mean, if you move to another point, it doesn't work. So this is why I said that the training data set that we have is quite robust. And we started now. Before, impossible.
Okay.
Thank you very much.
Thank you very much, Luke. Let's move on to the next speaker.